Welcome to Inorganic Chemistry. Today we are diving into the shapes of atomic orbitals. If you have ever wondered what an atom actually looks like on the inside, you are in the right place. We are going to build this understanding from the ground up, visualizing the invisible homes where electrons live. To start, imagine taking a long exposure photograph of a firefly buzzing inside a dark jar. You would not see a single clean path, but rather a blurry, glowing cloud where the firefly spends most of its time. An atomic orbital is exactly like that glowing cloud, but for an electron. Electrons do not orbit the nucleus in perfect, flat circles like planets around the sun. Instead, they buzz around in three-dimensional regions of space. The shape of an orbital is simply the three-dimensional shape of that blurry probability cloud where the electron lives. Now that we understand what an orbital is conceptually, let us look at how quantum mechanics defines it. Formally, an orbital is described by a wave function, represented by the Greek letter psi. By itself, psi does not have a physical meaning. But when we square it to get psi squared, it gives us the probability density. This is the exact likelihood of finding an electron in a specific tiny spot around the nucleus. Because the cloud technically extends to infinity, scientists draw a boundary surface diagram that encloses the region where there is a 90% chance of finding the electron. This brings us to the mathematical equation that defines these shapes. The total wave function of an electron depends on its straight line distance from the nucleus, r, and its angles in three-dimensional space, theta and phi. The function r of r is the radial wave function, which tells us how big the orbital is. The function y of theta and phi is the angular wave function. This angular part is entirely responsible for the actual three-dimensional shape of the orbital. As the angles change, this function dictates whether the orbital looks like a sphere, a dumbbell, or something more complex. Let us see how that angular wave function creates specific shapes, starting with the simplest one. When the azimuthal quantum number, represented by the letter L, is equal to 0, we get an s orbital. This orbital is perfectly spherical, meaning the probability of finding the electron is exactly the same in every direction from the nucleus. Think of it like a perfectly round tennis ball. As the energy level increases, such as moving from a 1s to a 2s orbital, the sphere simply gets larger, like inflating a balloon. Importantly, there are no angular nodes here, meaning no flat planes slice through the center. Moving up in complexity, when the shape code L equals 1, we get a p orbital. Unlike the perfectly spherical s orbital, a p orbital has a specific direction and looks like a dumbbell split into two distinct lobes. Right between these two lobes, exactly at the nucleus, there is a nodal plane. A nodal plane is a flat, invisible sheet of space where there is absolutely zero chance of finding an electron. Because three-dimensional space has three axes, there are three different p orbitals pointing in different directions, along the x-axis, the y-axis, and the z-axis. Continuing our journey through the shapes, when the shape code L equals 2, we get the d orbitals, which are even more complex. 4 out of the 5 d orbitals look like a four-leaf clover or a double dumbbell. The fifth one looks completely different. It resembles a standard dumbbell with a donut-shaped ring around its middle. These complex shapes have two angular nodes, meaning there are two intersecting flat planes where the electron probability drops to 0. These intricate shapes become incredibly important when transition metals form bonds, as the specific angles dictate how other atoms can attach. Before we move on to calculating nodes, let us see these shapes visually. On the screen, you can see the progression from the simple spherical s orbital at the top to the directional p orbitals in the middle, aligned along the x, y, and z axes. Finally, at the bottom, you see the complex d orbitals with their four-leaf clover and donut shapes. Notice how the p and d orbitals stretch out along specific axes? These distinct directional pathways are exactly what allow chemical bonds to form in specific geometries. Now that we have seen the shapes, let us look at a simple formula to determine the number of angular nodes in any orbital. Remember, an angular node is a flat plane or cone where the electron cannot exist. The number of angular nodes, which we will call A, is always exactly equal to the azimuthal quantum number L. This simple relationship allows us to instantly know how many empty planes slice through a specific orbital, just by knowing its shape code. Let us apply this formula with a concrete example. We want to determine the number of angular nodes for a 3p orbital. First, we look at the given orbital designation. The number 3 is the principal quantum number, which tells us the overall size of the orbital. However, for angular nodes, we only care about the letter p. The letter tells us the shape and gives us the exact value of the azimuthal quantum number L. Continuing with our calculation, we know that for any p orbital, regardless of its size, the shape code L is always exactly 1. By substituting this value of 1 into our equation, we find our result. This means a 3p orbital has exactly 1 angular node. In practical terms, if you look at a dumbbell-shaped p orbital, there is exactly 1 flat sheet of glass you could slide between the two lobes where the electron will never be found. Let us try a slightly more complex example. We want to identify the exact mathematical locations of the nodal planes for a dxy orbital. We know that the dxy orbital has 4 lobes that lie flat in the xy plane, pointing exactly halfway between the x and the y-axes. Because the lobes sit entirely between the axes themselves represent areas of absolute zero probability. Building on that setup, we need to translate those zero probability axes into 3-dimensional planes. The probability drops to 0 whenever the x-coordinate is 0 or the y-coordinate is 0 because the lobes never actually touch the axes. In a 3-dimensional coordinate system, the equation where x is 0 describes the entire flat yz plane. Therefore, the yz plane is our first nodal plane. Finally, we apply the same logic to the y-axis. The equation where y is 0 describes the entire flat xz plane. Therefore, the xz plane is our second nodal plane. This gives us our final answer. The two nodal planes are the yz plane and the xz plane. This perfectly matches our earlier rule that a d orbital, where L equals 2, must have exactly 2 angular nodes. So why do these shapes matter so much? Understanding the shapes of atomic orbitals is the absolute foundation of all chemical bonding and molecular geometry. When two atoms join together to make a molecule, their orbitals must physically overlap in 3-dimensional space. If we know the shape of the orbital, we can predict whether atoms will bump into each other head-on to form a strong bond or swipe sideways to form a weaker bond. Furthermore, pure atomic orbitals often mix together through hybridization, creating unique shapes like the bent structure of a water molecule. Let us summarize what we have learned today. Atomic orbitals are 3-dimensional probability clouds that show where an electron is most likely to live. We saw that s orbitals are simple spheres, p orbitals are directional dumbbells, and d orbitals are complex double dumbbells. These shapes are mathematically dictated by the angular wave function, and the number of angular nodes is always equal to the shape code L. Mastering these fundamental shapes allows us to visualize the invisible building blocks of the universe and predict how they connect to form everything around us. Great job completing this topic.